don't say anything you don't want to be recorded, and we'll wade into things. Okay, so let me go, and first thing I'm going to do is, and again, Daniel, thank you for doing that. I'm going to be sharing an application screen, and so what you're going to see is a PowerPoint kind of slide thing. And we'll see how I end up doing this. I guess I'm going to try to do it this way. That's a blank slide, but here is my outline of talking points for the day. And I'm going to share some good news and some, I'll call it other news. I don't want to say it as bad news. It's just news. It's sign of the times. So I'm going to do that. I'm going to do a little bit of cockpit commentary. You know that I fancy myself a bit of a pilot, and you guys are my passengers. And Jesse Hayes Carver is our very earnest and capable co-pilot in this whole thing. So anyway, I'll give a little bit of a cockpit commentary, and then I plan on polling you guys. And what that means is I'm going to call on each of you by name, and I'm really saying, okay, do you have any issues or questions you want to raise or concerns for the class? Now, if these are private concerns, this is probably not the place to do that because this is being recorded and everybody is listening. But I do want to do that, especially where we are and things like that. And the rest of these notes are useful for me. I'm just after we do the polling, I'm going to talk about, and maybe this is during the cockpit commentary, I'm going to talk about where we are and where we're going and things like that. And during this period, what I plan on doing is, and I know I discussed this before, but I'm only going to make you listen to me for 75 minutes at a stroke. So we're going to do 75, we'll do a 10-minute break, and then we'll come back and we'll do the balance of the 25 minutes. And you guys are supposed to get 100 hours of quality education per week. And that's what I intend to give you. So anyway, that's what's going to happen. All right, so now what I'm going to do is I'm going to advance this slide, and I'm going to talk about what is the good news. And I am going to read this to you. Now, this was an email that came out this morning, just a little bit before 8 o'clock. And in fact, it was a little bit interesting because this, I was here in the Learning Commons working, and it turns out that I can see Dr. Caputo through my window when he comes in, and he came in, and in fact I chatted with him about a couple of things, but one of the things that I did is I said, oh, this is really good news. So I am going to read this to you. Now, this doesn't say this went to students, but I'm sharing it with you anyway. So College of DuPage Community, which is you. Over the past several days, the COVID-19 indicators, and this is true in Illinois anyway, have moved in an encouraging direction. Based on the trends, the college will resume regular in-person instruction on February the 7th. Now, that's not a change in plans, but this is a confirmation that yes, we really are going to be doing this. And I had some colleagues who were not sure that this was going to happen, so I consider it very good news. Dr. Caputo continues. Our objective remains to keep the college community as healthy and safe as reasonably possible. We will continue to monitor environmental conditions and plan future actions with that objective in mind. And this is, from Brian Caputo. Now, this is what I characterize as good news because I am much better in class than I am in this mode, and so that's good for me and probably good for you as well. So I consider this this good news. So we are continuing on plan, and we're only going to be doing this remote thing for another week because this February 7th is 1 week from today. So 1 week from today, I will be in whatever classroom we've been assigned, and we'll be having class in there, and that will be good. Okay, so I'm going to pause for a OB to 5 Mississippi. This isn't a change of plans, but it is a confirmation of the new plan. So I'm going to count to 5 in my head, and if anybody wants to comment or ask a question about this, they can. Okay, I didn't hear anything, so I'm going to just assume that I'm still there with you, and that that will continue this way. So I'll go to the very next slide. Now, this is news, and it's not bad news, it's not good news, it's just news, but it's something you need to be aware of. And I learned this morning in my Calculus 1 class that many students didn't know about this. And so, I don't know what that means, but anyway, and some students had some question about it. So I'm going to read this and show you a thing, and then we can have discussion around this if we need to. Now now I was aware of this before, and in fact, I think I shared this with you before in either videos or something. But anyway, this came from Diana Del Rosario, and Diana Del Rosario is the assistant provost, and that means she's administrator here at the college. So anyway, and she called this student message 12822. Now, the way I'm reading this is that means that the way I'm understanding this anyway, that means that they sent you this message being a student in the class on 12822, which I guess was, I don't know, this is 31st, so it probably was last week. But anyway, they said COVID testing or proof of vaccination needed. Now, I am going to read this. And wow, it says that there was something below that, but I'm not, I'm not sure if she attached it or not. Anyway, this is what she sent to me and other faculty members. Okay, the message below was sent to students registered for spring 2022. So that is you. And scheduled for face-to-face and hybrid courses starting February the 7th, reminding them of how to get ready to be in compliance with the COVID vaccination or testing requirements ahead of coming on campus next week. And these messages were being sent by the Dean of Students. This is Nathania Montez, and contact information and links to the processes to be used are included in that note. So anyway, and I'll say a little bit about this, not a lot. But students who are not in compliance, that is not cleared. So you see everybody is either cleared or not cleared to be on campus as a result of not loading their vaccination card and or completion of the form that goes with it, or not completing the shield testing on campus, are encouraged to visit the student vaccination compliance page on our website. There is a link there for and they can receive additional support through her office. Thanks for supporting our communications efforts. Okay, now I'm going to tell you what this means. And again, you got a letter that's supposed to say this, but I do want people to understand this. Okay, so there are two ways that you can be what is called cleared. And on my class roster, next to your name is a designation. And so you are either cleared or you are not cleared. And the College Uta page is asking faculty to hand out cards to the people who are not cleared. Now, I think and I don't think I have any Jonies in this class, so I'm talking about a hypothetical Joni, and I apologize if there is a Joni in this class. I could tell you stories about someone I knew named Joni, but anyway, there is not a Joni, so consider this a hypothetical Joni. I am uncomfortable handing in front of the class, handing Joni a thing, because then people say, oh, bad Joni, she's somehow, something is wrong with her, she's not cleared, or whatever that is. But so what I've decided to do, and I'll say a little bit more about this, But when we meet next Monday, I will have these little cards or little forms, whatever they are, and I will have them for everybody in the class. Now, so Joni, let's suppose that Joni, for whatever reason, the hypothetical Joni is not cleared. And I don't think we have any, wow, I got to be careful about this. I don't think there are Jonahs in this class, and if there are, I apologize. But let's suppose Jonah is someone who is cleared. Well, both Jonah and Joni are going to get forms from me because I'm just going to pass it out. Now, this is not a bad thing because it'll help me, understand names, and I'll say, "Hey, Joni, where are you?" And then I'll hand you your form, and then I will hand the form to Jonah whenever I find Jonah there. Now, on Jonah's, in my little narrative, Jonah is a cleared person. And so I'm just going to say at the top of Jonah's form for only Jonah to see that, yeah, Jonah, my records show that you are cleared. Good for you. And on the hypothetical Joni's form, it's going to say, oh, Joni, you are, according to the records, you're not cleared. If you don't know what this means or what to do about that, you can talk to me, but you're not cleared, which is a bit of a problem. I mean, or at least it could be. You have to take action. And again, their database might not be clean. There can be all kinds of things, but you need to get this squared away because this is important stuff. It's about public safety, and the college is taking this very seriously. Now, there are two ways that you can be cleared. One way, and this Dr. Del Rosario wrote this with kind of double negatives here, and I don't know if that's easy to understand or not. But one way is you can turn in your vaccination status, official documentation of your vaccination status, to the college, and they record it, and then they list you as cleared. Now, the other thing that you can do is that you can get and undergo weekly testing. Now, that means you have to be testing on a regular basis because you might be sick one time and not sick another and things like that. So anyway, there is shield testing on campus. Now this is and I walk past this every day. It is in SRC, Student Resource Center, room 2000. And they have multiple lanes and you can go in there and get tested. Now, if you got tested, so for example, and I don't know exactly how it works, but if you went in there today, let's say you could get tested. And then they would take your information and they would send you a record of your test, and they are supposed to then send the College of DuPage a record of your test saying, oh, um, whoever is doing this testing thing, they say, yes, this person tested fine, they're safe to go to class the following week, and then the college would put you being cleared onto the thing. Now, you would only be cleared for that week because if this is the way you're going, you have to keep testing and so on and so forth. So anyway, that's what's going on, and I told you how I'm going to deal with it, and I'm just telling you that the college is taking this very seriously. Now I'm going to show you one more chart, and then we're going to, I'm going to pause for a second, and not a second, for more than a second. I'm going to pause in case anybody's got any questions about this. Okay, so now this is something that's torn off Blackboard, but if you go onto Blackboard and you look in the upper, I'm going to say upper right hand corner, you'll see something like this. So there's like a video, and Nathaniel Montez gives a little speech on this video and things like that. And this is a place where you can get more information and get engaged to this. I've already told you what I plan to do, so no one's going to be embarrassed. But also, before I teach this class next Monday, I'm going to go to my roster, and I'm going to print it out, and I'm going to print out those little forms, and everybody gets a form, and that'll help me learn your names and your faces. So I mean, that's not a waste of time that way, and then everybody knows what I'm telling them about their vaccination status. Or at least let me say your compliance status. It's not your vaccination status, it's just your compliance and cleared. So that's what I'm going to do, and that's how it's going to work next week, and I hope for the rest of the term. So actually, if I had to share my hopes, what I would say that I would hope would happen is that COVID would be, sort of banished from Illinois, and we would be in, good shape, and we wouldn't have to do this all the time, but we're going to be doing it on the 7th and maybe for a while. Now I'm going to pause for a count of 10 Mississippi, and I'm going to stop sharing this, and I'm going back to the I don't know what to call this, the Blackboard thing anyway. So I'm not sharing. I'm here, and if anybody wants to offer comments or raise their hand or say anything questioning about this, I'm going to count to 10 Mississippi. I will say 1 Mississippi and 2 Mississippi, just to give you time if you want to ask some questions about this. Okay, no one asked any questions, and that's all fine. So I'm going to go back to my talking points and just go from there. Okay, so I talked about, oops, that's the wrong one. That's actually my calculus lecture. Hold on, here we go. Okay, so that is good news and other news. All things considered, I'm happy about where we are, just really continuing my aviation analogy. I think we're approaching our cruising altitude and speed, which is good. And we had kind of an abrupt thing, and it was kind of a steep climb, and but we've done some things, and I deliberately decided to talk about separable equations first, and then I talked about homogeneous equations. And again, these are kind of
Are we supposed to
standard.
be seeing something?
Someone's trying to say something, so
Are we supposed to be seeing something?
you are supposed to be seeing something, so I need to fix that. Sorry about that. And thank you for dutifully doing your what I asked you to do. So thank you, Danielle. Okay, you are supposed to be seeing something, and so now what you should be seeing is a PowerPoint slide. Okay, or it's not in slideshow mode, but anyway. Okay, so we started, and I think you can see me waving my cursor here. So anyway, we started and we talked about separable equations because I thought it was really dry to begin talking about just the definitions and stuff. They're important and they're part of our vocabulary, but I said, let's solve some equations first. So we talked about separable differential equations, and I think we kind of beat that to death. And then we talked about another thing, which I think is useful, and I think we're going to see another example of this today, because what we said is, well, here's a different class of equations that aren't separable, but if we do something clever, a clever substitution, we can change them into separable differential equations. And again, that's something we often do. And in fact, we're going to do that again today. What we're going to do, at least I expect we'll do this today, is that we'll talk about this Bernoulli differential equation, which is one smart substitution away from being a linear first order differential equation. And we did talk about linear first order differential equations, and I did go back and post videos about definitions and such. Now, I'm not, I mean, I don't think it's a disaster or anything else, but this probably wasn't as smooth, but I told you to keep your seatbelts buckled, so I think it's all okay. I was this weekend thinking more about linear algebra than I was about differential equations. And then after my calculus lecture this morning, I looked at differential equations. I thought, damn, I didn't post a bunch of stuff I said I was going to post. So anyway, I had posted things, and in fact, I had posted the first wave of these definitions, but I hadn't posted the second wave. So more of the definitions were posted. I also realized I had not posted the recording of the video from last week, where we actually talked about linear first order, and I told you, oh, I'm going to post a lecture on that. Well, I hadn't done that. But now what I did, and I piled a whole bunch of stuff up there, and I realize I don't expect you to have watched this yet necessarily. It's really great if you did, but it's there. But anyway, so there are lectures on separable, homogeneous. So there are two lectures about definitions and so on, concepts. There's two lectures, I think, on linear first order differential equations. And I think there's two lectures on Bernoulli, and I think there is one lecture on exact differential equations. Now, those are video lectures, and they are what they are, but also they're not bad if you watch them as active learners. But we're going to be doing, some of this stuff today. And what I came prepared to do during our first 75 minutes, of which I've already spent 23 minutes of that, talking about other kinds of things, but I'm not worried about that either, because I've got this complimentary video thing going on, and it's okay. What I'm prepared to do once I finish the polling is we're going to work some more linear first order differential equations, and we're going to work some Bernoulli equations. My guess is that we will not get to exact equations during today's lecture, but that's okay because I'll pay attention to where we are. So with that, I am prepared to stop sharing here, and I am going back to let's see, I'm going to look at this. I'm going to look at the attendees list, and I have some alphabetical orders. I thought we had 9 students, but maybe I don't know. I hope people haven't dropped, because I will teach you a good course, and I know how to make this work. But anyway, now Daniel, you are first alphabetically on this list, so that's the reason I'm going to you. I'm just asking, is there anything you want to ask as a question, anything you want to share with the group or share with me? Again, it's not any private thing, so if Daniel had some private issues, we say, well, talk about that outside of the class. But anyway, so Daniel, first of all, how are you and yours? And do you have any questions at this time?
I think I'm doing all right. Starting to get the hang of the problems. So I just need to watch the videos, or at least work on some problems, and I'll be good to go. And also, there are just 7 students. The ninth one is Jesse, and last I checked, he's not a student. Not exactly.
Yeah, he's not a student. So okay, but I consider myself blessed to have the 7 of you, or the 8 of you, or however many there are. I guess it's 7, but that's good. And again, I'm bound to teach you a good course. And you were talking about Jesse, and again, I would really encourage you, if at all possible, for you to engage with Jesse, because I think that can really be worth your while. He's a good man. Okay, so Daniel, you're good to go for at least now, yes? All right, excellent. I will now go to Danny Janiak. And Danny, the same question of you. I'm saying, hey, how are you and yours? And do you have any questions or comments or issues you want to share with the class at this time?
I'm doing well. I don't really have any questions.
Okay, and that's good. Your questions and any student's questions are always welcome. Okay, so please feel free to ask those. Okay, that is good. Eleanor, we go to you next alphabetically, and so my question is, how are you and yours? And do you have any questions or issues or concerns or anything you want to raise either with me or with the class at this time?
Yeah, I had a quick question about the low stakes assessment. I know I saw something about something being due like next week. Do you have like a certain day we're getting that, or how is that gonna work?
Yeah, and I thought, I'm going to tell you what it is, okay? And I thought, and again, Eleanor, when I say I think, I sometimes have vivid dreams, in fact. So, so I mean that I'm glad you're raising this. It is going to be due on, and my plan was for it to be due on February the 7th. And I'm still going to have it be due on February the 7th. Now, that allows you and your classmates to say, oh, and I can just turn that in class on February 7th, because according to Dr. Caputo's thing, we're going to be back in class. Now, I had made provisions, at least in my head, I had made provisions for you to turn it in this way. And I think, and maybe I'm going to just, throw it out there. I thought in some video or somewhere I did talk about it, but let me tell you what it is. And I am making a note, Eleanor, based on your question. And maybe this is what I will try to do during the break. I will try to post it as an LSA in your syllabus tab. And do that. But let me tell you what it is. It is one problem. It is a modeling application, and I don't remember for sure. I'm going to make up some numbers. The numbers may or may not be the right numbers. But I say, oh, gee, you have a snowball, and so there is a snowball, um, and the snowball is a certain diameter at a certain time, and I'll just say time t equals 0. The snowball has a diameter, and I'm going to throw out 10 centimeters. I need to think about that. Is that a big snowball? No, that's actually just a kind of almost a regular snowball, because 10 centimeters isn't, I mean, that's not a gigantic thing. Okay, so anyway, it's 10 centimeters, but this snowball is melting. And so I will tell you that what is it? And please don't quote me on these numbers, because these might not be the right numbers, but I'll say something like, oh, it's 8 inches 5 minutes later, or something like that. So then I'm going to ask you, when will the snowball completely melt? Now, what this is going to require you to do, and everybody else, and again, it's not going to be something that's, and in fact, having it available for you today, I mean, you've got a week to do this, although I expect that most students are going to want to be going off and doing a lot more work than just this LSA. So what you're going to do is you're going to have to model this. And this gets modeled a little bit differently than the carbon-14 decay problem that I asked you before. Again, it involves, rates and things like that, but you want to think a little bit about the physics and the engineering of this. And again, this has take-home protocols, and that means that you and everybody else can work on it together. Okay, if you want, and so someone could ask, or you could go and talk to Jesse Hayes Carver about it, and you'll come up with some kind of a model. And then I'm asking you to solve the differential equation that you end up modeling this with. And I guess I'm giving away copious hints here, but I think that it is I think it is a separable differential equation, so it's something that you should know well how to solve. So anyway, I am going to I will double check, and I mean, I think in my own head I'm thinking I talked about that either on a video or in class, but I will post it separately, and I'll send you guys an email and an announcement saying it is posted there. So that's sort of my response, Eleanor, to your question. Did that help?
Yeah, I clarified things. Thank you so much.
Okay, and I'm going to assume that there's nothing else, but certainly feel free to speak up. Okay, we will go to and I picked up an action item of something to do during the break, so that's good too. Okay, Fazan, please. How are you, and do you have questions or issues you want to raise with me or with the class at this time? Okay, he is good. And sometimes students have technical difficulties. In fact, I had an issue with my mic apparently this morning. I don't know. I got it back and I fixed it. I may have just been, I don't know, drinking a cup of coffee or something and not been close to my mic. Okay, so anyway, Fazan is okay. We will go to, I think the name shows up as Jonathan, but I think he said he goes by John. John, how are you and yours? And do you have any questions or issues with the class you want to raise with with me or with your classmates at this time?
I'm doing well, and I don't have any questions at the moment.
Okay, excellent. That is good. Um, and by the way, I'm observing that a lot of people aren't showing me their face, which is fine. And you might say, "Oh, Jim, you're not showing us your face either." That's actually because I'm working in the Learning Commons, and I'm working in the Learning Commons, and I'm sort of by myself, but I'm working in a place that does not have a webcam on it. When I work from my home, which I sometimes do, I do have a webcam there, and so and it works for Zoom anyway. I don't know if it works well for Blackboard Collaborate, but anyway, I'm not much to look at anyway, so that's kind of okay. So John, you're okay. I'm going to Rohin, Kartik, Narayan. So Rohan, how are you and yours? And do you have anything you want to raise with me or with your classmates?
I'm good. I do not have any questions at the moment.
All right, excellent. Please ask the questions if and when you have them. Okay, and then we go to Victor Campos, please.
I don't have any questions. I am a little bit behind on the videos to watch, but I think I'm making good progress, so I'm okay.
Okay, well, engage you, and again, I mean, please do not, and not just you, but no one. I mean, gee, that was abrupt and probably not being a graceful pilot this morning because I kind of you said, oh, and we're changing our direction this way. So I did, you know, throw a bunch of stuff in there this morning, and you know, and it really would have been better if I'd done that, you know, like last Friday or something like that. But what I'm really saying is, you know, watch it at your earliest convenience, whatever that is. And I am waving at one one of my faculty mates, so across the way, they came into the Learning Commons. Okay, that finishes all you guys. Now you can always ask questions, and please do, but we're going to go and we're going to do some work during the balance of the period. And okay, so I'm going back to this. We're going to talk about linear first order differential equations, and I call this a chalk talk. Now, so what I'm going to do is I am going to share a whiteboard with you, and I'm just going to remind you of things. Now, if you are caught up on the videos, you say, yeah, I know all this, but I'm just reminding you so that this makes some sense as we go ahead. And I am going to give you a problem. So this is a little bit of the chalk talk about first order linear differential equations. First of all, what do they look like? They look like this, and that is y prime. So that is taking the derivative of that, and this is y prime plus, and I might not be using the same notation that I did before, but this is a of x, which is a function of x that's there, and then I have y, and this is equal to then f of x. So this is what you're supposed to have. Okay, now this is called your standard form. And I am going to be typing under here something about standard form. Standard form. I am typing, but the way Blackboard works is I have to finish typing before I can make it available to you. So this is called the standard form. Now, often you will not have the problem presented to you in the standard form. But what you want to do is you want to recognize that, oh, I can change this into the standard form. And if you are following the solution technique that I am describing to you, then you have to pay attention to the standard form. And details really, really matter. One thing that I will tell you a lot of students screw up with is the SIGN in this. And by the way, if you screw up the SIGN and you follow the recipe I'm doing, it won't work. Okay, and so you'll get the wrong answer. So the form really matters. And the reason we call it first order is the derivative is the first derivative. That's the highest derivative that we see. So it's y prime. We're going to be solving this for y prime. And this is called linear because every term has either a derivative, well, it's linear because there's only one y in each term, and the first term has y prime, that is a derivative of y, and the second one has a function, but notice that this is a function just of x, just of my independent variable, times the y, and it is plus a of x times the y, and y is the 0th derivative. And then you have this is equal to f of x on the other side. So this is called, and we talked about, you know, those in the definition video, but this is a linear first order differential equation. And the cool thing about linear, in fact, maybe I should write that down too. This is the standard form, and it's the standard form of a linear first order differential equation. And you might say, well, isn't everything linear? No, not at all. In fact, we solved nonlinear equations already in this course because most of those separable equations that we solved were non-linear kind of things. But this is linear first order differential equation. So this is what it looks like. And a key element in the solution of this is what we call an integrating factor. And I'll make a note about an integrating factor here too. Okay, and here is what the integrating factor is. And the integrating factor is, and again, it's really important, my students, that you are thinking about the standard form, because if you wanted to invent your own way of solving these, that's okay, but you have a different recipe and a different standard form. So anyway, the integrating factor for this, and what you're going to do is you're going to multiply both sides by that, and that will make this an exact differential that you can solve, is going to be, and the integrating factor usually is, and I guess I'm going to do it this way, it is mu, and mu is a function of x. And in most books, and in fact in your book, they call that mu, and of course that made it look like I was 2 years old when I wrote that. So we have a mu of x, and I did lecture on this, you know, in the videos and things like that. But this is mu of x, and this is equal to, and this is going to be, and I'm going to write this as exp, just so you don't get this confused. But this is e as the base, and then the exponent is going to be the indefinite integral, and we can take the constant to be 0, but this is a of x dx. And so what happens is you're going to multiply both sides by mu of x up here. And when you multiply all the way through by mu of x, that will, as we discussed in the video and otherwise, will turn this into an exact differential that you can solve. Okay, and so that's kind of it. I am going to say one more thing about this, and that is over here. That coefficient is 1, and a lot of times some of the pre-processing is you have to divide by whatever the coefficient is there to get that done. Okay, so this is kind of the chalk talk that I had, and what I'm going to do is I'm going to snip this into the PowerPoint slide. Okay, so I will save that, and then I'm going to the PowerPoint slide. Don't worry, Daniel, about, I'm just kind of doing some things, and I'll be back sometime soon. So the chalk talk is here, and so now I've changed that that slide, and I am going to go back now and share the application screen with you. And so, and Daniel, you don't have to respond unless you're not seeing it. This is like a PowerPoint slide, and I got some of the things that I wrote on the chalk talk and in here, and again, I just was reviewing that for you. Okay. Now I'm going to, and this is something I really do in class a lot, and I'm going to try to do it now just because I'm saying, hey, we will get into class. I'm going to ask you to solve this example 1 that you should see. Now, and I'm going to give you, I'm going to say 5 minutes to solve this whenever I say go. But this is a differential equation. It is y prime minus y minus x e to the x is equal to 0. And so I'm asking you to solve this. And so everybody should jump in and solve this. And I am going to ask, because I'm not always 100% sure, but I don't think I solved this before with you. I think this is a new problem, just because I was remembering where I got things from. So I'm hoping this is a new problem. If this is not a new problem, people should tell me. So please dive in and solve it. And I'll give you 5 minutes. And so in 5 minutes at 1:49 by my clock, I will come back and we'll look at a solution. And you might say, well, I don't know if I'll have time to solve it. Well, it really helps you understand the solution if you try to solve it now. So everybody, I encourage you to do that. And at 1:49, we'll return. I mean, I'm going to be here the whole time, but you should work to solve this. So everybody give it a go, please. Okay, my clock has turned over to 1:49, and so I'm going to declare this done. If you solved it, congratulations. If not, you thought about it and you'll learn something when we go through it. Okay, so I am going to, and I stopped sharing, and I'm going to be sharing a whiteboard. Okay, and I'm going to erase all of this. I'm going to kind of power erase it. And the first thing that one must do is you have to turn this into the standard form. So I'm going to write what you get when you turn it into the standard form. So you get y prime, and then it is plus, and I'm putting a -1 here. Now you don't have to write it that way, but you have to think about it this way because that's -1, and then the f of x is x e to the x on the other side. Okay, so now we got it into the standard form. That's an important first step. But then the role of p of x is being played by this now -1. So that means that what we need to do is we need to find our integrating factor. So that means that mu of x is equal to, the base is e, but the exponent is going to be -1, and this is dx. Now, when you integrate -1, you get minus x, and I told you that you could take the constant to be 0. It's simpler computationally if you do that. And so this means that mu of x is e to the minus x. So that means, at least according to the theory, if we take mu of x to be e to the minus x, I can multiply all the way through both sides by this, and I can have an exact differential. Now, I'm actually a pretty good mathematician, and I'm pretty good with calculations, things like this, but I'm going to tell you, I always check this to make sure that's true. So I'm multiplying by e to the minus x on both sides. And I realize I'm going kind of slow on this, and we talked about this some last time, but a little bit of repetition doesn't hurt. So we have e to the minus x times y prime plus, and then we have, this is -1 e to the minus x times y is equal to, and if I multiply e to the minus x times e to the x, e to the times x e to the x, I just get x. Okay, now the thing that I check is, according to the theory, this should be the derivative, or I'm going to say the differential, of minus e to the minus x y. And if it's not, something went wrong, and maybe I screwed up my integration or something like that. And you see it is, because this is the product rule. So this is the first times the derivative of the second plus the second times the derivative of the first. But when I use the chain rule, I'm going to get e to the minus x times -1. So you see, we're in good shape with this, okay? And so now we've turned this, using the integration factor, we've turned this into an exact differential. Now what I'm going to do is integrate both sides. And so when I integrate this side, I will have e to the minus x. See, when you integrate d something, you just get the something times y. And then this is equal to, and on this side, it is x squared. And I know I had a little bit of a discussion, if memory serves, it was with Eleanor, but whoever it was, you do have to have this constant. And in fact, this time, you're going to see that the constant really is quite important. Now, this is where I'm putting it. And you do have options about where you put it, but that's where I'm putting it. But now, usually, you want to solve for y. And so now I'll solve for y. And the way I'll solve for y is by multiplying both sides or dividing if you want to. And you can divide by this because the exponential is never 0. So I'm just going to multiply by e to the x both sides. But notice that now what I get then is I get e to the x times x squared plus c. And that is the general solution that we have for this differential equation. And sometimes I will ask you, what is the interval of validity? And you say, well, when does this solution make sense? And you would say here, this solution makes sense from minus infinity to plus infinity, because when I solve for that, that always makes sense. E to the x has a domain of all real numbers, x squared has a domain of all real numbers, and things like that. And in many applied problems, and I'm looking ahead, but we will have this e to the x or e to the minus x, whatever it is, ends up being part of a transient solution. And so you'll have a steady state and a transient solution. So you see this constant of integration is an important kind of thing. Now, so I think I may have a comment there, and yeah, Daniel has raised his hand for a comment, and then I'll check the others. So yes, Daniel, what's up?
You integrated x, so wouldn't it be x squared over 2, or did I miss
It's
something?
supposed to be x squared over 2. I screwed up. Thank you. And thank you for paying attention. That's great.
I just compared our works.
Yeah, well, and of course, and by the way, you should definitely ask those questions and so on and so forth. And so that's good with this one. Other comments or questions on this one? Okay, we're going to declare that that was good, and now we're going to do another one. So I'm going to use the, let's see, do I want to try to cut that and put that on the other one? I don't know. I'm doing something, and so I'm not, I mean, I know I'm talking to you, but I'm not trying to show you anything. Oops, that was dumb, Jim. How do I undo this? I don't know how to undo that now. Hold on. Okay, I keep doing, we're not going to do that. I'm just erasing that. Okay. I was trying to do something fancy. Let's go to another problem. And here is the next problem we're going to do. I am not going to ask you to do this, but certainly this is another one. And if you're taking notes and you say, oh, I want to go back and you know, solve this one later as practice or something, you certainly could do this. But this is not in the correct form for a first order linear differential equation according to the recipe that I have. And so what you need to do is you need to move things around here a bit. And in addition to moving things around, and I think maybe I need to go, oh, I bet I didn't share my screen with you. I didn't do that.
Yeah.
Hold on, let me fix that. And that's, okay, so I need to think about this. Hold on. Share application screen, and we go there. Thank you, and thank you, Daniel. You were very good at this. I'm not going to I'm going to try to remember not to make you do it all the time. Okay, now you should be seeing
Yeah, I
a
don't care.
differential equation, and this is different. Okay, so does x y prime equal y plus 2x cubed? But what the serious student should do is he or she should recognize it. Well, yeah, but this is linear first order. I just have to reorganize it to use my recipe. So one thing you're going to do is you're going to divide all the way through by that x. Now, when you do that, that means that you're saying, oh, x can't be 0. So that is going to have an influence on your work going forward. But that's one of the things you do to get it in the form. And then you have to move, you know, things across. and so on and so forth. So you'll have minus 1 over x times times y plus, and then this is going to be 2x squared is going to be the other side. So you have to massage this, and certainly you could do this, but I don't think we're going to spend time doing it. But I'm going to pause for beta 5 unless people didn't understand what I was trying to say. Okay, that's excellent. People are at least saying they do. Now here's another one that's similar, and this is really in much the same form as the first one, actually. This time we're going to have p of x being a minus 2. But again, I don't think that adds a lot. I'm looking for something that we can do, and this one is you're going to divide all the way through by x squared. You're going to put the minus 2 on the other side because that's your f of x, and you're going to have 1 over x, but it's plus 1 over x. And again, I don't think that this is, I mean, again, you can certainly solve this, but here's a problem I want you to, and I think this is the one I do want you to do. Yeah, let's do this one, okay? And I'm going to give you 5 minutes to do it. But this is involving trig functions, and in addition to having trig functions, you might notice that, oh, there's an initial value here. That means that you can figure out what the constant must be. So everybody give this a go. I'll give you 5 minutes. It's 2 o'clock right now, and so around 2:05 we'll talk through this solution. So please give it a go, and at 2:05 we'll reconvene. Okay, it turned over 2:05, so I'm going to stop sharing this. And I'm going to go back to the thing and try to share a blank whiteboard with you. And I'm just going to talk a bit about all the highlights of the solution or something like that. First of all, the integrating factor, or the mu of x, then, is going to be, and this is going to be e, and this is going to be minus, and this is the integral of the tangent of x dx. Okay, now you have to remember how to integrate the tangent, and that is going to be okay, so I guess I'll say here, this is going to be then equal to, this is e, I'm taking the constant to be 0 here because I can, and this is minus the absolute value of the cosine of x. But then I'm going to realize that e and the logarithm are inverses of each other, and I have this minus sign here, and so that says that this is going to be so the integrating factor then is going to be and there's a minus, excuse me. There's this minus and this minus will cancel, so I get that. So what I'm multiplying by is the absolute value of cosine of x. So if I go back to the problem, then what will be happening is I'm multiplying all the way through by the cosine, and so what I will get is so the solution is going to be, and I need to remember what my original differential equation was, and I'm just going to show you that. I am mindful of the time. If I have to talk a little bit past the break, I'll give you your full break. But I'm sort of jumping around amongst my notes here. Okay, so the original equation was, what we have is, this is y prime times cosine of x and then it is going to be plus, and then this is going to be y times, and this is going to be the sine of x. I think I lost a minus sign here. I need to put it back in. This is the sine of x over the cosine of x. But I'm multiplying by the cosine of x. And let's see, and that is going to be, there was a minus sign there. I'm going to fix that with my eraser. There was a minus sign there, so that is that's really good. I do need the minus sign, so I do have the minus sign there, and these will cancel. And on the other side, then I have, let me remember what I had on the other side. Oh, I had sine of x. And this is sine of x now times cosine of x. Okay, now this is the differential then, and again, I told you I would check it. I usually will. So I'm checking it here. So this is the derivative of y times the cosine of x. Okay, so that is because that would give me minus sine y, that gives me all this. And that's equal to this sine x cosine of x. Okay, so when I integrate both sides, I'm going to get y y times the cosine of x equals, and when I integrate this, this is 1/2 the sine 2x, so this I think is going to be 1/4 sine 2x. Wait, that's sine 2x, that's 1/2 sine 2x. So when I integrate it, I'm really getting cosine of 2x. So I'm going to erase that and do it right. Okay, so okay, so I get that y of x is equal to, let me just do y. I'm so excited about being back into class. This will be a lot easier then. So I'm going to get that this is 1 over 2 cosine x times this integral. And this is the integral of 2 sine x dx. That's using the trig identity that sine x times cosine x is 1/2 sine of 2x. And so I'm just going to, and then we have an initial condition. And so what I am going to do is, let's see, can I do that here? Okay, I'm going to, you substitute the initial condition in, and you can figure out what the constant is. Now I'm going to erase this and just go on to the final page, and I'm going to write what the solution is. So the final solution you should have come up with, including figuring out the constant, is that y as a function of x. And you could write this differently, and I will always figure out if you have the right thing. But this is 5 minus cosine of 2x all divided by 4 times the cosine of x. Now, sometimes, and I realize I didn't ask you about the interval of validity, but now I am going to do this. You see, our thing was originally at 0. Our initial condition was y at 0 equals 1. And one of the things that we've learned, at least I've talked about it in the videos, and I think I've talked about it here, but what you need to do is you need to stay away from this being, and so 0 is your, 0 has to be in the solution. So I'm looking at the real number line, but you see this will not work if I go up to, let's see, I'm looking for a solution, and so 0 is there. That's where the initial value is 1, but I can't have this denominator go to 0, so this will go up to pi over 2. So an interval of validity for this differential equation is from 0, no, hold on, I have to include 0. I'm saying something wrong. I'm going to erase this now. So I have to include 0, but I pick the biggest one I can. And so what I really want to do is go to minus pi over 2. Wait a minute, that's not making that 0. I'm changing my mind now. This is 4 minus cosine x. That's never 0. Forget all this. The interval validity for this, I was actually thinking I had a cosine in that denominator by itself. I don't. And that denominator is never 0. So the interval validity That would have been an interesting discussion, except I wasn't paying attention to the numbers I had. So this interval validity really is going to be from minus infinity to infinity. Okay, I'm going to pause now and count to, I know it's 2:15, but I'm going to count to 10 Mississippi in case people have questions, and then we're going to do something else at the end of this. Actually, we're going to do one more example after the break of this, but then we're going to do something else. So I'm counting to 10 Mississippi in case there are questions. You will get your full break, so if you have questions, please ask them. Okay, we will reconvene at, I will call it 2:26. So at 2:26 by my clock, we'll reconvene and we'll work for a while longer. Okay, we're on break now. Okay, my clock says it is 2:26, so we're reconvening. And here's the last problem that we're going to talk about, at least during this segment, about linear first order differential equations. And so I call it example 7, but I say find the general solution of this differential equation that you see here. So y is equal to 2y to the fourth plus 2x whole times y prime. And I'm going to give you, I'm going to say 3 minutes to work on this, or maybe no, I'll give you 5. So go ahead and get started on this, and I'll give you 5 minutes, and that means at 2:32, I'll call it quits at that, and we'll go through and talk about a solution. So please give it a go. Okay, my clock says it is 2:32, so I'm going to stop sharing this, and I'm going to go to the whiteboard and share a blank whiteboard. Now, this was, and again, I'm not trying to trick you, but this problem was different because it turns out this is not linear in Y. So I'm going to make that comment here. So this is not linear in Y, but here is what is true. This could be reorganized in the following way. So I could consider this where, and again, it is a little bit arbitrary, if X is the independent variable or Y is the independent variable. And what we can learn is that it can be arranged as d x dy minus 2 over y times x is equal to 2y cubed. But, so the answer, or I don't know, I don't want to say the answer, but it is a linear first order differential equation in X. Okay, so there's the words that I have, so we have that. And your integrating factor this time would be mu of X, except it's not mu of X anymore, it's mu of Y. And that's going to be equals, this is e to the minus the integral, and this is 2 over y. And actually, see, I have to deal with this minus sign here, which is what I'm doing. That is dy. And if you think about this is you're going to have a natural logarithm here, but you're also going to have a negative exponent. So this ends up being 1 over y squared. So that is your integrating factor. And so what you end up with, and I don't have a lot of room here, so I'm just going to abbreviate it. But what you'll end up with is 1 over y squared times x. And this derivative that I'm showing here is really the derivative with respect to y is equal to, and this is 2y. So then when you solve this, you'll get for your solution that x as a function of y is equal to y squared times, and this is y squared plus c. Okay, so I'm going to pause for a count of 10, Mississippi, in case people will want to ask some questions about this or something like that.
Relatively quick question. How did you go from dy dx to dx dy?
Okay, I mean that's a good question, but I guess, and I'm going to try to answer it this way. Now, you might not find this satisfying, and if not, I have to, maybe I'll do something a little different. But dy dx, and you learned this from your calculus, I think this is actually calculus 1 at the College of DuPage, but and again, what I'm writing is you have to In fact, I'm going to write this differently here. And that's not what I wanted to do. Let's go to the eraser. This is a theorem that you learned in Calculus 1. I'm doing it the wrong way. Over here, I should have written it this way. Now, these are different points that they're evaluated at, but this is dx dy. And so I'm not knowing, Daniel, if this is like ringing a bell. You used this when you were finding the derivative of inverse trig functions and things like that.
Just take the inverse of both sides and then work from there, right?
Yeah. Now, the one thing I wanted to make clear is that on one side, you're putting AB as the point. On the other side, you're putting BA as the point. And I'm trying to give you like a rationale for this as well, not just quoting the theorem. But this thing that I'm drawing dotted is supposed to represent the line y equal x. So what happens is, I'm just using an example here, but that is the exponential function, but this one is that. So if I'm talking about the derivative at this point, there's a place over here where the derivative is also the same value. And if the point up here is AB, actually, maybe I could just do it this way. The other one is BA. So like this is 0, 1. And this is the 0.10. And so those derivatives are the same. I know my drawing doesn't look like it, but those derivatives have the same value. Is this ringing a bell at all, Daniel, or is this not good for you?
Yeah, it's ringing bells.
Okay, good.
Plus, it also makes sense to just flip it.
Yeah, and the flipping, and by the way, engineers sometimes, and again, I'm not being critical of engineers. I love my engineering students, but sometimes they like to treat infinity like a real number, and it's not. And a lot of times that doesn't get them into trouble, but sometimes it does. So, but yeah, you are flipping it. But what you should be able to get is this, and all I'm really trying to emphasize is it's useful to solve this problem, that way. Okay, I'm going to pretend that that's good, at least for now. Feel free to ask other questions. And when a student asks a question, I usually start my count over again. So I'm doing my count of 10 Mississippi again.
Just a clarification question on the second step. After you flip the y to 1 over y and the derivative thing inverse that way, it's derivative of x. Would the 2y to the 4th plus 2x be by itself a fraction, or would it be 1 over 2y to the 4th plus 2x?
I'm not ignoring your question. I'm trying to, I think maybe, I think algebraically, this is correct. So because you see, here's the 2x right here, and I had to divide by a y because there was a y over here, And so this is what we get when we divide the 2y to the 4th over, divide that by y, I get y cubed. Maybe I'm not understanding your question. Can you pose it again, please?
I was mostly just trying to figure out how we went from the given equation to the equation that you currently have an arrow pointing to.
Okay, let's go back and do that. So I am, all right, so okay, so let me go back to the original equation, which was, and I got to dig through my notes to get at that one.
Y equals 2y.
Yeah, go ahead. Go
So
ahead. So it's y equals, and I'm going to write what you say. Go ahead. It's y equals.
then in parentheses, 2y to the 4th plus 2x. Close
2y
parentheses, y prime.
to the 4th plus 2x. Okay, and then this is y prime here.
Yep.
Okay, great. Okay, so what I'm going to do then is I'm going to divide all the way through by y. Okay, so when I divide all the way through by y, I will have 1 equals, and by the way, if it reaches a point where you don't want to hear any more of this, we can do that, but this is 2 y cubed. Okay, actually it is 2, I'm dividing by y, and this is plus, and this is 2x over y, and I have y prime here. Okay, now what I'm going to do is I'm going to solve for, so this is and y prime is dy over dx. Okay, so I'm going to move this to the other side, and so this is dy over dx. So what I'm going to do then is I'm going to move this to the other side, and so this is 1 minus, and this is 2x over y. So I've moved that to the other side, and this is dy dx. And this is equal to 2y cubed. Now I think I'm good so far. Okay, so then I'm going to solve this for dy dx. So dy dx
Now I think
is equal to, and I'm sorry, this is so, I know it looks like I'm a 2-year-old writing here.
Don't
This
worry,
is
that's my handwriting too.
2y cubed plus 1. Okay, and then let's see, and let's see. So then I put that on that side, and this is going to be minus 2xy. Now I'm going to turn both sides upside down. So dx dy Yeah, Daniel, go ahead.
What I was just wondering is, how did the 2x over y have the dx dy, but not the 2y cubed?
Because now I'm talking about how I went from this step to this step. Okay, I just divided all the way through by y. So here I divided the 2x by y in that term. And here, oh, I should have had a y prime there, you're right. Okay, so that changes the way I saw it. Yeah, you were correct. You were correct. So, so this is going to be, I'll tell you what I will do.
I do think I get where it's going to go at this point, so I think I'm good.
Okay, well, okay, and what I will do is, since I didn't do that very smoothly, I'm just going to erase this. Okay, and I've only got a couple of more minutes in the period before we're finished for the day. So I am going to stop sharing this and go back and share the application screen just for a moment. And I'm going to show you, if you don't get this, we'll talk about it tomorrow or next time, and maybe I'll write it up more nicely. But I am going to go here, and I was going to do a chalk talk about this. I still am going to do a chalk talk about it. Okay, so here is a very short chalk talk about this equation. I got just one shot to give, and I'm not going to do the chalk talk there. I'm going to stop sharing there. I'm going back and I'm sharing the whiteboard just a little bit. This is what a Bernoulli equation is, and I do this much better in the video, but it looks like this, or can be made to look like this. So that is a of x, and at this point in time, you're saying, well, that just looks like what we did. But now the other side is this, which is b of x, but now this is y to the n. Now this y to the n term is what makes it Bernoulli's equation, and this is a wildly non-linear thing. But here's the substitution that we're going to do, and if you watch the videos, you'll see about this, and we'll talk some more about this next time. But this is the substitution that you use. It's z equal y to the 1 minus n, and then this becomes linear, first order, and then you'll reduce the substitution. So we will talk more next time about Bernoulli equation. I encourage you to watch the videos, and we'll talk more about this, and we'll do other things next time. And Eleanor, I also got involved in other things during the break. I had a faculty member come past here, and I ended up talking to them. So I will clean up the LSA thing, as well as maybe deal with Daniel's question before next time. Okay, so you guys take care, and I will talk to you on Wednesday, and hopefully that's the last time we'll do these remote things. Everybody take care, and I will talk to you soon. Bye-bye.
Just so you know, I did figure out how to do the problem. It was a simple matter of moving the dx dy over through multiplication and division. And he's gone.